direct thermal charging cell for low-grade heat to electricity conversion. Okay, so as you know, a large amount of low-grade heat exists in the environment and usually in the form of waste heat in industrial process, and efficient conversion of this low-grade heat to electricity is still challenging. So solid-state thermoelectric devices such as a bismuth telluride utilize the electrons or electron holes as the energy carriers, which work on the temperature difference between two heat reservoirs, have been studied as major candidates for heat to electricity conversion so far. However, the low feedback coefficient, or we can call thermopower, usually in the scale of 100 to 200 microvolt per Kelvin. So as a result, to generate a useful voltage of around 1 to 5 volt in the low-grade heat region requires either challenging integration of thousands of thermoelectric elements or use a DC-DC voltage booster to increase the voltage. So with the current materials, solid-state thermoelectric semiconductors working within 100 degrees C have an efficiency less than 1 or 2%. And recently, liquid-based thermoelectrochemical cells, TEC, utilize ions as the energy carrier and attract increasing attentions due to its thermal power can be larger in the level of millivolt per Kelvin. And compared with thermoelectric semiconductors, you can think nature offers only one species of electrons, but the numerous species of ions. So we have people have a lot of choice to manipulate this system. And the high thermal power is coming from the large entropy changes in the electrochemical system. And the incorporation of an electrochemical system also offers new opportunities to engineer the entropy change, thermal and electrical transport. So as you can see here, thermal galvanic cell can be used to generate voltage under thermal gradient, but the poor ionic mass transport between two electrodes causes a poor efficiency. So the TEC can also operate in a thermal cycle, where the connection to the hot or cold reservoir alternating as a cycle in this way. So in this case, the pouch cell configuration can be used, which can significantly reduce the distance between two electrodes to improve the ion transport. So there are also another approaches to use this ion diffusion effect we call solar effect. So usually, the operation mechanism in the thermoelectrochemical system, using the thermogalvanic effect or solar effect, then the operation mode can be used like a thermal gradient or the thermal cycle. But so far, to date, the conversion efficiency of TEC technology, the efficiency is still too low, or the system is too complex for the practical applications. So here in this work, we invent an electrochemical device called direct thermal charging cell, DTCC. We use graphene, oxide, and platinum nanoparticle as a cathode, and a polyaniline as a conductive polymer as anode, with an aqueous iron-based redox electrolyte, and use a pouch cell as the packaging. So far, DTCC reaches highest heat to electricity conversion efficiency as compared with other systems. So we publish paper and file the patent. So as seen, there are 3 stages during operation of DTCC. So initially, there is a built-in voltage between two electrodes because this is asymmetric electrodes. And when heating, the thermo-pseudocapacitive effect of graphene oxide generates a thermal voltage. And this open circuit voltage will be further increased by redox couple in the electrolyte, as you can see here. So, and when connect the external circuit, the voltage drives the oxidation of polyaniline anode to release the electrons. So the electrons will be then carried at the cathode side by redox couple in the electrolyte. So after the reaction stop, because the iron 2 plus is already deployed in the system. So, and based on our design, the system actually can be regenerated when cooled down for the next cycle. Because of the catalytic reaction between the redox couple and the oxidized polyaniline. So I will explain a bit more later on. So as seen in this slide, the mechanism, first, heating causes the thermal charging process at the cathode side, and the cell generates voltage via temperature-induced pseudocapacitive effect of graphene oxide and the thermogalvanic effect of iron 2 plus and iron 3 plus. And then the VOC should be higher than the onset voltage of polyaniline to drive the oxidation of polyaniline. So the discharge continuously by oxidizing polyaniline and reducing the iron 3 plus under isothermal heating until the iron 3 plus depletion. So this is the second step. And then finally, the cell can be self-regenerate when cooled down, and then back to the original status for the next cycle. So this is the basic mechanism of our design of DTCC. So in the detail of the experiment, so at stage 1, as you can see here, the thermal response can reach about 5 millivolt per Kelvin, so which is 200 times higher than the Seebeck coefficient in thermoelectric semiconductor. And the thermogalvanic effect of redox couple will boost up the open circuit voltage, as seen and compared with figure C and figure D. So this is without redox couple. This is with a redox couple. So our voltage can be boosted up to 400 millivolts at the 90 degree C. Okay, so the thermally induced pseudocapacitive effects coming from the functional groups on graphene oxide. As you can see, there's two typical reactions here. So at stage 2, heating at 70 degrees C can generate the open circuit around 350 to 400 millivolt, and the discharge can be performed at isothermal heating condition. So this is the experiment by using 3 electrode system with a reference electrode use. So as you can see here, basically the voltage, the trend of the voltage follow the cathode, and our electron actually most of the current provided by the anode side of the polyaniline. So right now the DTCC can be operated at the low-grade heat regime properly, and the optimal operating range is about like 40 to 90 degrees C, because the open circuit voltage of the cell has to be larger than the onset voltage of the polyaniline to make the polyaniline being oxidized and release the electrons. So that determine the threshold temperature. So the about like 30 to 40 degrees C. So, and the upper limit is due to the use of aqueous electrolyte here. So because of the water evaporation. So, and as you can see here, so at stage 1, open circuit voltage is generated by graphene oxide thermo-pseudocapacitive effect majorly, and the stage 2, the oxidation of polyaniline and the redox couple reactions contribute to the current output. So at stage 3, as you can see here, after cool down, so the iron 2 plus. So because at the stage 2, so it will stop because all the iron 3 plus will be becomes iron 2 plus. So and the polyaniline be oxidized. So the here, the iron 2 plus and oxidized polyaniline when cooled down, so they have a catalytic reaction, this effect in the acid environment. So our electrolyte is in the pH value is about 3 to 4, so this acid environment. And this catalytic reaction will happen to make the polyaniline being reduced back, and also the iron 2 plus and reduced back to the iron 3 plus, oxidized back to the iron 3 plus. So this system can be chemically regenerate and back to the original system for the next cycle. So this allows our system can do the cycling performance. Okay, so right now in the lab we can do 20 cycles with a good temperature response, as you can see here. And in our startup company, we can now make over 500 cycles already, and we also try to improve our targets over like a few thousand cycles for practical application in the future, hopefully. And the DTCC reaches the highest performance as compared with other thermoelectric systems. The heat to electricity conversion efficiency is around 3 to 5%, and its ratio of Carnot efficiency can reach over 30%, as you can see here. So this is the demo of using DTCC and the wrap on the hot pipes about like 50 degrees C, as you can see here. The voltage generated is about 2.7 volts, so which can light up OLED. So this is OLED, and also can power a small electrochemical film, as you can see here. Yeah, so this is the demonstration in our lab. Okay, so now we are working on the new electron materials with a higher thermal power, and also the gel type or hydrogel electrolyte to improve the cycling performance and also widen the operating temperature window. So, and which can be used for a higher or lower temperature range. So this is the new material we are working on. So if compared with a commercial product usually used currently, is a thermoelectric semiconductors. So DTCC is cheaper and high efficiency. So in low-grade heat region. So it uses a thermal cycle rather than the temperature cycle rather than temperature gradient. So which is good because it is challenged to maintain the temperature difference across two electrodes, particularly when the temperature is low. So, and also DTCC have a unique advantages, including a high efficiency, low cost, and a bendable nature, and also technical simplicity, and also the ability to form stacks of cells. So so that's why support by Hong Kong government, we established a startup company and being selected to enter the Hong Kong Science Park. So we also finished the first fundraising, and then now we have industrial and business partners. We hope to make our academic research to have real-world applications. So we attend many entrepreneurship competitions and won awards, hopefully to attract more investors and customers. So currently we engage 3 industrial partners. So first is a Hong Kong-based HVAC company. So our idea is to recover the waste heat from air conditioner. So as you can see here, so the temperature of HVAC compressor is about 55 degrees C, so it can be recovered and generate electricity. So the second company is in Taiwan. So the company is producing electrochemical window. So our idea is to integrate our DTCC module into the window frame, and which can absorb the solar heat and generate electricity to power and change the color of smart window. So this can make an off-grid smart window system without using socket. So this is our lab demo. So we use about like a 60 degrees C hot water. So as you can see, it can change color of the electrochemical window. And this is our prototype. And right now it's under testing in Taiwan, Kaohsiung. So the third company is in Shenzhen. So we are thinking to harvest the human body heat to power sensors by using our new DTCC system and using new materials. So this is the preliminary electronic design. So this is our lab demo. As you can see, the new type DTCC can generate voltage from human skin about like 32, 33 degrees C, and that is enough to power some low power consumption sensors. And this is our prototype of flexible DTCC, as you can see here. So now our business center is located in Hong Kong Science Park, and our manufacturing site is in Taiwan. So we finish 10,000 class clean room and a pyron line with a 200-liter mixing tank for graphene oxide and polyaniline slurry and paste fabrication. So we also produce DTCC modules now. So in 2020 Q1, we received the first revenue of around 2 million Hong Kong dollars. And also we have signed a contract with the Hong Kong Electrical and Mechanical Service Department, EMSD, to test the reliability of DTCC module in the green roof of EMSD headquarters. So the test will run for 1 year. We also signed some NDA with different companies for product development. For example, like a listed company, Tongpo in Hong Kong. So this is my group. Thanks for their hard working in this project, and also thanks for funding support from Hong Kong government and the industries. So, and this is the end of my talk. So I'm